right? So in the last class we discussed liquid solution containing two liquids, that is liquid in liquid solution, liquid in liquid, liquid in liquid solution, which means your solute is liquid, the solvent also liquid, that's the meaning, right? So if I take, suppose I'll take two liquids, right, liquid A, and I'll take another liquid, say liquid B. I'll take two liquids. Okay, first I'll take pure liquid A. Okay, I'll take pure liquid A, right, and I'll keep the solution at some temperature T, right? You know very well the liquid, assume that the two liquids are volatile, right? Assume that both are volatile liquids. Both are volatile liquids. So in this container we have only pure liquid A. So the liquid evaporates, then condensation will occur, then you will get an equilibrium. At equilibrium you measure the pressure above the liquid, that corresponds to vapor pressure of pure liquid A. Vapor pressure of pure liquid A. Similarly, you take another container, okay, and take pure liquid B in this, pure liquid B, right? Here also you'll get evaporation occurs initially, then condensation takes place, then the system will attain equilibrium. At equilibrium, at the same temperature T, measure the vapor pressure of this liquid. This is vapor pressure of pure liquid B. Now if I mix these two, liquids, I will get a solution. I'll get a solution which consists of the liquid A and liquid B. Okay, then this vapor above the liquid, this also consists of A and B, right? Both A vapors and B vapors will be there, so we have a mixture of vapors. In this mixture, what is now listen, the temperature is same again. Here also the temperature is same temperature, right? So at the same temperature, what is the pressure exerted by A alone and pressure exerted by B alone in this liquid mixture? Okay, for this Raoult gave a law called Raoult's law, R-A-O-U-L-T-S, Raoult's law. What Raoult's law says is that the vapor pressure of, or the partial vapor pressure exerted by A alone, right? Partial vapor pressure, okay, exerted by the component A alone, which is represented as PA. PA means partial vapor pressure of A in this mixture or in solution. This is directly proportional to mole fraction of A present in the liquid phase. Okay, so in the liquid phase, let us say the mole fraction of A is XA and mole fraction of B is XB. Okay, so XA, XB are mole fractions of A and B in the liquid phase. Okay, according to Raoult's law, the partial vapor pressure of A is directly proportional to mole fraction of A present in the liquid phase. Similarly, the partial vapor pressure of B is directly proportional to mole fraction of B present in the liquid phase. So if I equate this, we have to introduce a constant, and that constant is nothing but vapor pressure of pure A into mole fraction of A. Similarly here, vapor pressure of the partial vapor pressure of B, right? If I equate proportionality into equal, we should introduce a constant. That constant is nothing but vapor pressure of pure B into mole fraction of B, right? This is what we call as Raoult's law. Raoult's law, right? And if you know the partial vapor pressure of A and partial vapor pressure of B, you can say what is the total pressure, okay, above this mixture or above the solution, right? So what is the total vapor pressure? Total vapor pressure above the solution is nothing but partial vapor pressure of A plus partial vapor pressure of B. Okay, this is actually the total pressure obtained by using Raoult's law. Okay, whenever you use Raoult's law, we call this pressure, if you use Raoult's law and calculate total pressure, we call that total pressure as theoretical total pressure. It is actually theoretical total pressure. Okay, so this is very important, keep this in mind. This is what we discussed in the last class, right? If you take liquid in liquid solution, okay, assuming both liquids are volatile liquids, right? You take the pure liquid A and pure liquid B, measure their vapor pressure, right? Let the vapor pressure is P naught A and P naught B. Then you mix the two liquids, you will get a solution. So this solution, okay, consists of two liquids A and B. Both are volatile, therefore both evaporates. So in the space above the liquid, you have vapors of A as well as vapors of B. So you will get a mixture. Now, what is the total pressure? How to calculate the total pressure theoretically? Yes, you can calculate the total pressure theoretically by using Raoult's law. Okay, I am going to say that, yeah, this Raoult's law is valid for ideal solution, right? We are going to discuss that, okay, as we go along. But before that, let me tell you what is the Raoult's law. What is Raoult's law? Raoult's law is very simple. Listen, at a given temperature, the partial vapor pressure exerted by a component, okay, is directly proportional to the mole fraction of that component present in the liquid phase. Okay, here we have two components in the solution, A and B. So partial pressure of A is directly proportional to mole fraction of A. Similarly, partial vapor pressure of B is directly proportional to mole fraction of B. Right? If we equate this, if we convert proportionality into equal, we should introduce a constant. That constant is nothing but vapor pressure of pure A. Similarly, this is vapor pressure of pure B. Okay. So if you calculate the partial vapor pressure of A and partial vapor pressure of B using Raoult's law, and if you add the two, you will get total vapor pressure. This total vapor pressure is theoretical total vapor pressure. This is theoretical. Okay. Now what I am going to do, let me tell you another important point here. Yeah. Now we'll discuss about the different types of solutions. Okay, let me take the first one. See, we classify solutions. We classify solutions into two. Right? Number one, ideal solution, and number two, non-ideal solution. Okay, non-ideal solution. We have two types of solutions, ideal and non-ideal. First, let me take ideal solution. Okay, ideal solution. Then we'll discuss about non-ideal solution. Right, what is ideal solution? Students, observe this carefully. Suppose I'll take two liquids A and B and I'll mix them. Okay, so I'll take liquid A and liquid B. Okay, I'll mix them so that I'll get a solution. I'll get a solution of A and B. Okay, I'm taking liquid A and liquid B, I'm mixing the two, so that I'm getting a solution. And assume that both are volatile liquids. Both are volatile liquids. Volatile means it will become vapor readily. That's the meaning, right? Both are volatile liquids. Now, what I'm going to do, what is the total vapor pressure? Okay, so we have solution now. We have a solution which consists of A and B in the liquid phase, and A and B also there in the vapor phase. Both liquid A and B all evaporate and occupy the vapor, occupy the empty space. So vapor also consists of A and B, liquid phase also consists of A and B. That's the meaning. So we have a solution. At temperature T, okay, I'll calculate the total vapor pressure using Raoult's law. Okay, so using Raoult's law, or according to Raoult's law, let me use the term like this, using Raoult's law. Using Raoult's law, I'll calculate the total vapor pressure. What is the total vapor pressure? Total pressure, right? Total vapor pressure above the liquid is equal to partial vapor pressure of A plus partial vapor pressure due to the component B. Okay, if you add the two partial pressures, you will get total. Right? And you know very well, this is nothing but theoretical vapor pressure. Whenever you use Raoult's law, it is called theoretical. It is called theoretical total pressure. Theoretical total pressure. Okay. Now, according to Raoult's law, partial pressure of A is nothing but vapor pressure of pure A into mole fraction of A, and partial pressure of B is nothing but vapor pressure of pure B into mole fraction of B. Right? So total vapor pressure, right, is equal to the sum of these two quantities. If you use, see, this and these are obtained from Raoult's law. If you add the two, you will get total vapor pressure, and this total vapor pressure is nothing but theoretical vapor pressure. Now what I am going to do, I am going to measure the pressure of the vapor through some using some instrument. I am going to measure. Actually, we have an instrument called manometer. Using the manometer, we can measure the actual pressure of the vapor above the liquid. Okay, let me call that vapor as the observed pressure or experimental vapor pressure. So what is the observed total pressure? Observed total pressure means pressure measured through experiment. Okay, let me use that as P observed. Observed, right? Observed total pressure. So P observed is the observed total vapor pressure, experimentally determined total vapor pressure. Now what I'm going to do, I'm going to compare these two. This is theoretical. Okay, this is theoretical. Let me put theoretical here. This is theoretical total pressure, and this is observed total pressure. Now I'm going to compare these two. Right? Suppose if these two are equal. Okay, let me write in the next page. If total pressure observed means experimentally measured, if it is equal to the total pressure that is calculated using Raoult's law. Okay, if these two are equal, we call that solution as ideal solution. Students, note down, very, very important. If the experimentally measured total pressure is equal to the theoretical total pressure, right? Theoretical total pressure means total pressure measured using Raoult's law. If these two are equal, we call that solution as ideal solution. Okay? Now, okay, the solution is called ideal solution. If it is an ideal solution, right? So if these two are equal, then I can say simply the total pressure is equal to partial vapor pressure of A plus partial vapor pressure of B, which is also equal to P naught A into XA, right? From Raoult's law, PA equal to P naught A into XA, and from Raoult's law, PB equal to P naught B into XB. These two we know, okay, from Raoult's law. Now, in the last class, you know very well, since the solution consists of only two components, so mole fraction of A plus mole fraction of B should be equal to 1. And using this relation, last class we derived this, the expression, that is P naught A plus P naught B minus P naught A into XB. We have derived a relation like this. Okay, total pressure. Students, observe carefully. This total pressure, right, is nothing but theoretical total pressure, and for ideal solution, theoretical total pressure and observed total pressure are same. Observed means experimentally measured, okay, and this is theoretical. If these two are equal, we call the solution as ideal solution. Okay, so for ideal solution, you can calculate total pressure using this formula, right? And in the last class, I told you that if this formula is obeyed, right, if this formula is obeyed, then we call the solution as ideal solution, right? So what is an ideal solution? What is an ideal solution, right? Ideal solution, solution which obeys Raoult's law. Students, observe this carefully. Solution which obeys Raoult's law under all proportions, under all compositions. Okay, whatever amount of A and B you take, okay, whatever amount of liquid A and liquid B you take, right, all composition in all the mixtures, right, the solution obeys, if the solution obeys Raoult's law, we call that solution as ideal solution. So what is an ideal solution? Solution which obey Raoult's law under all compositions, composition is called an ideal solution. That's the point. Is this clear, students? It will obey Raoult's law. Okay, solution which obey Raoult's law under all compositions is called an ideal solution, right? And for ideal solution, you can calculate the total pressure using this formula, and that this total pressure, also called theoretical total pressure, and the observed pressure are actually equal, right? Maybe roughly equal also, you can say equal or roughly equal. We call the solution as ideal solution, right? Now let me give some important characteristics of ideal solutions. Okay, what are the characteristics? So for ideal solution, so as I told you, ideal solution obeys Raoult's law. Ideal solution obeys Raoult's law. Since it obeys Raoult's law, we can say that total vapor pressure equal to P naught A plus P naught B minus P naught A into XB. It obeys Raoult's law, so you can calculate the total vapor pressure using this formula, right? And for ideal solution, we all know that total vapor pressure, which is measured experimentally, also called observed, and the total vapor pressure which is calculated, okay, calculated or theoretical, whatever maybe it is, theoretical, these two are equal. If these two are equal, we call the solution as ideal solution. Okay, so for ideal solution, these are all some of the characteristics. It obeys Raoult's law under all composition, right? Then second point, students, observe this carefully. For ideal solution, see, we are taking liquid A, we are taking liquid B, both are volatile liquids. If you mix them, you will get a solution. Solution containing A and B. Right. Now, in pure liquid A, we have only A molecules. So there will be some attraction between A molecules. So here you have force of attraction between AA molecules. You have some force of attraction between AA molecules. Similarly, in pure liquid B, we have force of attraction between BB molecules. Okay, in pure liquid A, we have force of attraction between AA, and in pure liquid B, we have force of attraction between BB. Students, turn on your camera, everyone. Turn on your camera, yes. So in pure liquid A, we have force of attraction between AA molecules. Okay, I am representing that as FAA. And in pure liquid B, we have BB molecules. Between them, there will be some force of attraction, which is I am representing as FB dot B. Okay. In solution, we have force of attraction between A and B. Force of attraction between A and B. Suppose if all these force of attractions are approximately equal, if force of attraction between A, if it is roughly equal to force of attraction between B, and it is roughly equal to force of attraction between AB. Okay, that is force of attraction between AA and BB and AB, right? All are roughly equal. If they are roughly equal, we call the solution as ideal solution. This is another way of saying ideal solution. This is one important characteristic of ideal solution. In ideal solution, the force of attraction between AA molecules and force of attraction between BB molecules and force of attraction between A and B are all roughly equal. Actually, we should say theoretically we can say they are equal, but for most mixtures, right, they won't be exactly equal, so they will be approximately equal. If they are approximately equal, we call the solution as ideal solution. Okay, this is one important characteristic of ideal solution. Then second point, since forces of attractions are all equal, okay, there is no see, by mixing the two, I am not getting some additional force of attraction. Force of attraction does not increase. Force of attraction does not decrease. Correct? I am mixing the two. I am forming a solution. Right? Force of attraction of A and B are roughly equal to these two. They are all equal. So there is no increase in force of attraction, or there is no decrease in force of attraction. Right? So from this, it is we can say that. Listen, suppose I'll take pure liquid A of some volume. Okay, let the volume of pure liquid A is VA, and I'll take pure liquid B. Let the volume of pure liquid B is VB. Right? I'll mix the two. I'm forming a solution. Let the volume of the solution, I'll say as, I'll write like this. Okay, this is the volume of the solution. I'm mixing A, some volume of A and some volume of liquid B. I'm mixing the two. I'm getting a solution whose volume is, okay, I'm representing the volume of the solution as VSOLN. Okay, solution. Now, before mixing, students observe carefully. This is after mixing. This is the volume after mixing. After mixing. This is the total volume before mixing. Correct? Total volume before mixing is VA plus VB. Total volume after mixing is V solution. Okay, or we can also write VAB, but it may give some confusion, so that's why I wrote V solution. Now listen, students, I'll write the next page. if the sum of volume of liquid A and volume of liquid B, this is total volume before mixing, and this is V solution, this is total volume after mixing, right? In the case of ideal solution, these two are equal or roughly equal. These two are equal or approximately equal. We call the solution as ideal solution. So in ideal solution, listen, delta V mixing. What is delta V mixing? What is delta V mixing? Delta V mixing means total volume after mixing. Total volume after mixing is V solution minus total volume before mixing is VA plus VB. Since these two are equal, so this quantity and this quantity are equal, delta V mixing is 0. Students, note down this, this is very important. For ideal solution, delta V mixing is 0. Why? Because there is no increase in force of attraction or there is no decrease in force of attraction. Force of attraction remains same. Therefore, the total volume before mixing, this is total volume before mixing and this is total volume after mixing. Okay, the two volumes are same. Therefore, the difference, right, total volume after mixing minus total volume before mixing, this difference is 0. Okay, so for ideal solution, keep this in mind. For ideal solution, delta V mixing is 0. Okay, so this is another important point you should keep in mind. Then third point, students, observe carefully. Okay, it's very, very important. Listen, we mix liquid A with the liquid B and we have formed a solution, right? We have formed a solution. Solution containing A and B. Okay. Listen, I have told you in liquid A we have some force of attraction between AA molecules, some force of attraction. In liquid B we have some force of attraction between BB molecule. If you mix the two, we'll get force of attraction between AB. For ideal solution, I have told you these are all roughly equal. These are all roughly equal for ideal solution. If they are equal, we call the solution as ideal solution, I told you. Now listen carefully. Students, suppose if the force of attraction between AB, suppose if it is increase, right? If it is increase, what does it indicate? The AB attraction is stronger, right? If increases means AB attraction is stronger. Whenever there is an attraction between two molecules or two species, listen, I'll take two species, okay, A and B. If the attraction increases, if the force of attraction, I will just write FOA. What is FOA? Force of attraction. If force of attraction increases, students, observe carefully. This is I'm giving this information just to understand this concept. If the force of attraction increases, right, whenever there is an attraction, okay, energy is released, okay, or heat is released, energy is released. Energy is released. Students, observe carefully. This is a general point that you should keep in mind. Whenever force of attraction increases, energy is released. Similarly, in some cases, right, force of attraction may decrease. If force of attraction decreases, that means repulsion is more. That's the meaning, right? Between A and B, repulsion arises. When repulsion exists between A and B, okay, or I can say force of attraction decreases. If force of attraction decreases, then energy is absorbed. Okay, students, is this clear? Keep this point in mind. Whenever force of attraction increases, energy is released. Whenever force of attraction decreases, energy is absorbed. Okay, if the force of attraction remains same, third point. If force of attraction FOA remains same, what is meant by that? Remains same, no change in energy, right? Or no release or absorption of energy, right? No change in energy, I can say like that. No change in energy E. Students, observe this carefully. If force of attraction increases, energy is released. If force of attraction decreases, energy is absorbed. If force of attraction remains same, no change in energy. So here force of attraction, right? AA attraction, BB attraction, AB attraction, all are same. There is no change. So in this case, there is no release of energy or there is no absorption of energy. So what I am trying to say is that delta H mixing. What is delta H mixing? That is total enthalpy after mixing minus total enthalpy before mixing. This is actually 0. Why 0? Because force of attraction between AA, between BB and between AB, right, all are same. Force of attraction between AB remains same, right? It doesn't increase or it doesn't decrease. It remains same. That means while mixing A and B, no energy is absorbed or no energy is released. So we can say that delta H mixing is 0. This is another important point for ideal solution. Students, is this clear? Any doubt here? Okay, if force of attraction increase or if force of attraction decrease, then you have to bother about whether enthalpy of mixing or whether heat is released or heat is absorbed. But in this case, all the force of attractions are same, so you need not worry about the enthalpy of mixing. Enthalpy of mixing should be 0, simple. Okay, then next important point. When you mix liquid A and liquid B and forming solution, okay, entropy, see, let me write like this: liquid A, I have liquid B, okay, forming the solution containing A and B, right? In the case of ideal solution, you know very well, the force of attraction between AA, BB, AB all are same. Therefore, the total entropy, okay, we use this symbol for entropy, S symbol, entropy symbol. Total entropy before mixing, okay, so let me say that it is a sum of SA plus SB. What is SA plus SB? SA plus SB is the total entropy before mixing. S A plus B, or let me write simply SAB. SAB is the total entropy after mixing, right? Since there is no there is no difference in the force of attraction, right? Force of attraction between AA, BB, AB all are equal. Since there is no change in force of attraction, okay, the total entropy after mixing and total entropy before mixing are same, are one and the same. Therefore, what is delta S mixing? I'm sorry, I made a mistake. I'm sorry. Here, so here delta S mixing, listen carefully. Here we have so before mixing the total entropy is this SA plus SB. After mixing the total entropy is AB. But here, since force of attractions are same, okay, so what will happen, as the number of molecules, right? Here we have only AB, Here we have more molecules, right? Right here we have separate A, separate B, so number of molecules are less. Okay, therefore the total entropy will be somewhat less. Whereas here the total entropy increases, right? Because more molecule in solution, we have more number of molecules. Both A and B are there. Here in pure liquid A, we have only A molecules. In pure liquid B, we have only B molecules. Correct? So the total entropy will be less. But when you mix the two, the total entropy increases. So delta S mixing is positive. What is delta S mixing? Okay, delta S mixing, why it is positive? Because delta S mixing is nothing but entropy after mixing minus entropy before mixing. Before mixing is SA plus SB. After mixing is SAB. SAB value is greater than this. Therefore, since this value is greater compared to the sum of these two, so this value should be positive. So keep this in mind. For ideal solution, delta S mixing is positive. That is, entropy increases. If you mix A and B, entropy increases. So delta S mixing is positive. Okay, then next important point, when you mix liquid A and liquid B while forming a solution, students observe this carefully. I am mixing A and B, I am forming a solution. If A and B mix and form solution, okay, spontaneously, we are not doing anything, right? We are just mixing. We are just mixing the two components, okay, mixed together and form homogeneous solution. Right? When you get a solution, that process is spontaneous. And you know very well, for all spontaneous process, the change in free energy should be negative. Right? So delta G mixing, okay, change in free energy for mixing should be negative. Why? Because this is, see, A and B forming solution. It forms. Suppose if A and B doesn't form solution, if the liquid A and liquid B form a separate layers, then there is no mixing. In that case, delta G mixing, okay, is 0 or positive. But A and B mix together and form a solution. This is happening. Okay, this process is spontaneous. It's a spontaneous process. Okay, if I mix A and B mix together and form solution. It happens spontaneously. For any spontaneous process, delta G should be negative. So delta G mixing is negative for ideal solution. Students, is this clear? Any doubt up to this?
Sir, what is delta G?
Delta G is change in free energy.
Okay, sir.
Change in free energy. For a process to be spontaneous, students, keep this in mind. Okay, if you want to identify whether a process is spontaneous process or not, calculate delta G. If delta G value is negative, that process is spontaneous. Okay, here if you mix the two liquid A and B, okay, the components A and B mix together and form a solution automatically. We are getting the solution, right? So that process occurs spontaneously. Therefore, delta G should be negative. Okay, delta G mixing should be negative. Right? I can say in the other way also. Students, this you can say in the other way. You know very well, delta G is equal to, from thermodynamics, we know very well delta G equal to delta H minus T into delta S. It's a formula, right? Delta G equal to delta H minus T into delta S. Okay, and we also know, yeah, this you can also write as, for solution we can also write this as delta G mixing equal to delta H mixing minus T into delta S mixing. Right? For ideal solution, students, observe this carefully. For ideal solution, delta G mixing equal to, what is delta H mixing for ideal solution?
Just now we discussed. What is delta H mixing? 0, sir.
Delta H mixing is 0 minus temperature T and delta S mixing. What about delta S mixing? Is it positive or 0 or negative?
Positive.
Yeah, this is a positive value. Temperature is always positive. Okay, because we give temperature in Kelvin. So temperature is always positive here. This is also positive. Positive into positive is positive. Positive into negative is what we'll get? Here I have negative sign. This is positive. This is positive. I have to multiply. Positive into positive is positive. Positive into negative is negative. Am I right? The overall is negative. Correct? Students, is this clear? Okay?
Yes, sir.
Yeah.
Yes, sir.
Take. So let me just summarize everything for ideal solution. For ideal solution, students, can anyone tell me what is ideal solution? What is ideal solution?
A solution which follows the Raoult's law over a range of concentration is known as an ideal solution.
Very good. Okay, a solution which obey Raoult's law under all composition, right? Under all composition. For ideal solution, these are all the points you should remember. Force of attraction between AA, force of attraction between BB, and force of attraction between AB, right? They are all roughly equal. Okay. Second point, delta V mixing, right? As there is no change in force of attraction, volume after mixing, volume before mixing, okay, are same. So delta V mixing is 0. As there is no change in force of attraction, delta H mixing also 0. Number 4, delta S mixing, okay, this is positive. Why this is positive? Because in pure liquid A, we have only AA molecules, so randomness will be somewhat less. Similarly, in pure liquid B, we have only BB molecules, so randomness will be less, okay, in general. But if you mix A and B, you have mixture of A and B, so randomness increases in larger extent. Therefore, entropy, total entropy of the mixture or solution is very high compared to total entropy of pure liquids A and B. Okay, therefore delta S mixing is positive. Then fifth point, delta G mixing, right, is negative because the two liquids mix together and form solution. It occurs spontaneously, so delta G mixing should be negative, right? So these are all the points you should keep in mind for ideal solution, right? And ideal solution obeys Raoult's law. Obeys Raoult's law. Is this clear, student? Any doubt?
Clear, sir.
No.
Okay, and remember, for ideal solution, theoretical total pressure. What is theoretical total pressure? Also called calculated, right? Calculated. What is calculated total pressure? Theoretical or calculated? Equal to P naught A. Yeah, remember this formula: P naught B minus P naught A into XB. Okay, theoretical total pressure, right, is this, and this total pressure is exactly same or roughly same as the observed total pressure. So this is very important. This total pressure, calculated or theoretical, is equal to total pressure which is determined experimentally, observed. Observed total pressure and calculated total pressure are equal. Okay, so this is the characteristic of ideal solutions. Okay, these are the points you should remember, okay, for ideal solution. Then I'll give one more point here for ideal solution. This is also important. students observe carefully, for ideal solution. Okay, now see, I have a solution, ideal solution containing two liquids A and B. Okay, and the two liquids evaporate, so I have component A and B in vapor phase also. So this is solution phase, liquid phase, okay, and this is vapor phase. So we have A, B in liquid phase as well as in vapor phase, because both are volatile. Now students, observe this carefully. Now the mole fraction of A and mole fraction of B in the liquid phase, I am represent the two mole fractions as XA and XB. The mole fraction of A and mole fraction of B in vapor phase, I will represent that as YA and YB. So keep this in mind. XA, XB are mole fractions of A and B in liquid phase. YA and YB are mole fractions of A and B in the vapor phase. Okay, now what I'm going to do, I'm going to give a relation between these two, right? Relation between, right, mole fraction, okay, in liquid phase and vapor phase or the gas phase. What is the relation between mole fraction in the liquid phase and the relation and the mole fraction in the vapor phase? Okay, how to relate them? Yes, listen, whatever that I am going to discuss here, it is applicable only for ideal solution. Students, keep this in mind. It is applicable only for ideal solution. Right? Now, for ideal solution, say this. According to Raoult's law, we can write that partial pressure of A is equal to vapor pressure of pure A into mole fraction of A, according to Raoult's law. Similarly, partial vapor pressure of B equal to vapor pressure of pure B into mole fraction of B. That we know. This is according to Raoult's law. Okay, since ideal solution obey Raoult's law, so these two are valid. Now, according to Dalton's law of partial pressure, according to Dalton's law of partial pressure, you might have heard about this in the in your 11th standard. According to Dalton's law of partial pressure, okay, suppose if the vapors A and B, assume that they are ideal gases. Okay, suppose assume that A and B are ideal gases. Okay, if the two gases A and B are ideal gases, then I can write the partial pressure of A, students observe this carefully, partial pressure of A is equal to mole fraction of A in the vapor phase into total pressure. So this is total pressure into mole fraction of A in the vapor phase. Similarly, partial pressure of B is equal to total pressure into mole fraction of B in the vapor phase. Okay, so YA, YB are mole fractions in the vapor phase, XA, XB are mole fractions in the liquid phase. Right? And remember, these two and these two are one and the same. Partial pressure of A, partial pressure of A. Partial pressure of B, partial pressure of B. What is the difference? Raoult's law relate partial pressure with the mole fraction in liquid phase. Dalton's law relates partial pressure with the mole fraction in the vapor phase. Since these two are equal, they are one and the same. So by relating these two, we can write see this quantity, that is P naught A into XA, should be equal to should be equal to this quantity, that is total pressure into YA. Students, observe carefully. This is XA, this is YA. So I am relating the XA and YA. Okay. Therefore, what is the mole fraction of A in the vapor phase? We can write this as, so mole fraction of A in the vapor phase equal to, see this, YA is equal, bring this total pressure down. So it's nothing but equal to vapor pressure of pure A by total pressure, right, into mole fraction of A in the liquid phase, in the solution phase. Solution, right? So I just brought this term, total pressure, to the left hand side. So P naught A into XA by total pressure. Okay, I wrote that like this. Students, is this clear? So if you know,
Yes, sir.
yeah, if you know, see this formula, very useful formula and very important for competitive examination. If you know mole fraction of A in the liquid phase, you can calculate mole fraction in the vapor phase if these two values are available. Right? Take down. Is this clear, student? Students, is this clear? Any doubt?
Yes, sir. Good answer.
Yeah. Similarly, by equating this and this, by equating these two, okay, this quantity and this quantity, we can write mole fraction of B in the vapor phase is equal to P naught A, I'm sorry, P naught B by total pressure into mole fraction of B in the liquid phase. Okay, take down. So if you know mole fraction in the liquid phase, you can calculate mole fraction in the vapor phase. These formulas are applicable, right, only for ideal solution. Only for ideal solution. These formulas are applicable only for ideal solution. Is this clear, student? Any doubt?
No,
Yeah.
sir.
Good. So this is regarding ideal solution. Now I'll give examples for ideal solution. This is also very important for competitive examination. They'll give two liquids and they'll ask you to identify whether the two liquid form ideal solution or not. Okay, so to identify that, keep this in mind. These are some important points you should keep in mind. What is that? Usually hydrocarbons, okay, if you have mixture of hydrocarbons, they form ideal solution. Mixture of hydrocarbon form ideal solutions. Say for example, N-hexane and N-heptane. Let me write here. N-hexane plus N-heptane. This is liquid A, this is liquid B. What is the difference? Here you have 6 carbon atom. Okay, 1, 2, 3, 4, 5, 6. 6 carbon atom. This is N-hexane. Here we have 7 carbon atom. That's all. 1, 2, 3, 4, 5, 6, 7. Okay, and you know very well this actually represent a formula, right? This is CH3 here. This end also has CH3. All the remaining ends have CH2. Here I have CH2, 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 CH2. So this is N-hexane, this is N-heptane. Both are hydrocarbons. N-hexane and N-heptane, this mixture forms an ideal solution. Okay, mixture of hydrocarbons usually form ideal solution. Similarly, I'll take another example. This is example number 1. I'll take another example. Say this is an hydrocarbon called benzene, and this compound is called toluene. Both are hydrocarbons. This is benzene, and this is toluene. toluene. Both are hydrocarbons, right? If you mix, generally if you mix hydrocarbons, you will get what is called ideal solution. So this will give you ideal solution. Benzene and toluene will give ideal solution, right? Students, take down. Is there any doubt, student?
No, sir.
Okay, yeah, take down. And the point is this: in N-hexane and N-heptane, the forces of attraction are almost the same. So if you mix them, okay, the mixture also have the same force of attraction. That's the point. But to understand this easily, you just keep in this mind. If we mix two hydrocarbons, okay, we usually get ideal solutions, right? Then second point, suppose if I mix compounds with the compounds belong to same functional group, compounds belong to same functional groups, especially halides, okay, say halides, alkyl halides, let me write like that, alkyl halides, okay, and aryl halides, alkyl halides and aryl halides, they usually form ideal solution, okay. But here alkyl halide and aryl halide, okay, you take two alkyl halide or you take two aryl halides, they usually form ideal solution provided the molecular mass should be close. Or I can say in the other way, suppose I am taking two alkyl halide, the difference should be very, very small. Difference in molecular mass, I'm sorry, difference in molecular mass should be very, very small. What is meant by that? See, I'll give an example. Example number 3. I'll take two alkyl halides, say for example N-butyl bromide. Students, see this CH3, CH2, 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 okay, Br. This is N-butyl bromide. Then I'll take another compound CH3, CH2, 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 same butyl group. Here also I have butyl group. Here also I have same butyl group. Now I'm going to add chlorine. This is N-butyl bromide and this is N-butyl chloride, or 1-chlorobutane, IUPAC's name, 1-chlorobutane, and this is 1-bromobutane, right? Same alkyl chain is there. What is the difference? Here I have bromine, here I have chlorine. So they are adjacent halogens, right? In the halogen family, chlorine, bromine are in adjacent position. Therefore, the difference in molecular mass is not very high. There is no huge difference, right? Some small difference is there. They form ideal solution, right? Similarly, I'll take aryl halides. Say for example, I'll take chlorobenzene. This compound is called chlorobenzene and this compound is called bromobenzene. Chlorobenzene and bromobenzene, okay, they are halides, aryl halides. These two are alkyl halides, these two are aryl halides, okay, and chlorine and bromine are adjacent halogens. Therefore, they form ideal solutions. Okay, students, are you able to follow this?
Sir, what is the difference between alkyl halide and aryl halide?
See here I have a chain of carbon atom, right? Here I have aromatic ring, benzene, right? Whenever halogen is connected to aromatic ring, we call those halides as aryl halides. Halogen connected to aromatic ring. Aromatic means benzene, naphthalene, anthracene, they are all aryl groups, aromatic. So whenever halogen is attached to aromatic group, directly it is called aryl halides. Whenever halogen is connected in chain, they are called alkyl halides.
Okay, sir.
Okay, yeah. So you take two alkyl halides. This is a liquid. This is also a liquid. Chlorobutane and bromobutane, both are liquids. If you mix them, you will get ideal solution. Similarly, if you take chlorobenzene and bromobenzene, if you mix them, you will get ideal solution. So the point that I like to say here is, listen, if you take mixture of two hydrocarbons, you will end up with ideal solution. If you take mixture of two alkyl halides or mixture of two aryl halides, okay, if the molecular mass is close, then they also form ideal solutions. These are all few examples for ideal solutions. Okay, similarly, I'll give one more example here. See this? This compound is called ethyl bromide. Okay, it's a liquid. Ethyl iodide, right, is also a liquid. If I mix these two, what will I get? See, I have same methyl group, same methyl group. Bromine and iodine are adjacent halogen atoms, adjacent halogen. Okay, therefore they also form ideal solution. Is this clear, students? Okay, so for ideal solution, to identify ideal solution, right, you just see the two liquids. If both are hydrocarbons, okay, blindly you can say it is ideal. Or if both are halides and see the formula, if they are close, yes, they form ideal solutions. Okay, is it clear, students? Right? Yeah, this is regarding ideal solutions. Okay, now let me go to the next one called non-ideal solutions. I'll just introduce this, then I stop. Non-ideal solutions. What is a non-ideal solution? Very simple. If the theoretical total pressure calculated means using Raoult's law. You calculate total pressure using Raoult's law, and you measure the total pressure through manometers or experiment, also called observed total pressure. This is observed total pressure and this is calculated total pressure. If these two are not equal, we call the solution as ideal solution. Students, observe carefully. If the two are not equal, it is ideal solution. If they are equal, if they are not equal, it is a non-ideal solution. If they are equal,
Ideal.
ideal. Okay, it's very simple. Now here there are two possibilities. Here there are two possibilities. What is that? Calculated may be greater than this, or calculated may be lesser than this. There are two possibilities, right? So if the total pressure observed, okay, experimental, I'll take this, right? If the total pressure, observed total pressure, if it is greater, experimental total pressure is greater than the calculated total pressure. If the observed total pressure is greater than calculated, okay, we call that solution as non-ideal solution. Students, observe carefully. Non-ideal solution showing positive deviation. Non-ideal solution showing positive deviation, right? If the total pressure observed or calculated, the experimental total pressure, if it is less than the calculated total pressure, if it is less, we call that solution, let me write here, we call that solution as non-ideal solution. Non-ideal solution showing negative deviation. Is this clear, student? So we are going to discuss non-ideal solution in the next class, but keep this in mind. What is meant by non-ideal solution? Very simple. You calculate the total pressure using Raoult's law and measure the total pressure experimentally. If the two are not equal, the solution is non-ideal. Okay, if the two are not equal, then two cases arises. What is that? If the observed total pressure may be greater than calculated, or observed total pressure may be less than calculated. Okay, if it is greater than calculated, we call the solution as non-ideal solution showing positive deviation. If the observed total pressure is less, then it is called non-ideal solution showing negative deviation. And remember, students, how to calculate total pressure? What is meant by calculated total pressure here? Calculated means calculated using yeah, very good. Yeah, it is nothing but P naught A into XA plus P naught B into XB. Or yeah, you are also right. You can also say like this: P naught A in plus P naught B minus P naught A into XB. This is also correct. Okay, these formulas we arrived using Raoult's law. Okay, so if you use Raoult's law and if you calculate the total pressure, it is called theoretical total pressure or calculated total pressure. Okay, observed means it is experimentally measured. Okay, if the experimentally measured pressure is greater than calculated, it is positive deviation. If experimental total pressure is less than calculated, it is negative deviation. Okay, yeah, students, I stop here. We'll continue this in the next class. Okay.
Thank you, sir.